two other properties that we need to know about elements and their trends, they're on the periodic table, are ionization energy and electronegativity. So the first one we're going to talk about is ionization energy. So ionization energy, the definition that you need to make a flashcard for, is the amount of energy required to remove an electron from an atom. And we can measure this in joules or kilojoules. And we can also measure what are called like the first, second, third, and on ionization energies. What this represents is what's the amount of energy required to remove the first electron, what's the amount of energy required to remove a second electron, a third electron, and on and on and on. In class, we'll talk about why those numbers vary, but for now, we need to know how does ionization energy change on the periodic table. So first, we'll talk about going down a group. So let's look at the diagram on the right. As you move down a group, so down the alkali metals, from lithium to sodium to potassium, what we can see here is all these elements have the same number of valence electrons. They have one valence electron. But as we go down the group, the size of the atom gets bigger. Potassium is a much bigger atom than sodium and then lithium. And as a result, the Coulombic force, the Coulombic attraction between the valence electron, which is negatively charged, and the positively charged nucleus decreases, because this distance, the length of this arrow here, is getting larger. So if you remember Coulomb's law, the relationship between attractive force and distance are inversely related. So for lithium, since the distance between the negatively charged electrons and positively charged protons is much smaller, since the distance decreased compared to sodium and potassium, the attractive force is much greater. So the flow of logic to explain this is, so as distance changes, so let's say as distance increases between, we're talking about the distance between a nucleus and a valence electron, okay, then the attractive force, or the Coulombic force, will decrease. And if the attractive force decreases, the ionization energy, again the amount of energy needed to remove that electron, is also going to decrease. So elements at the bottom of the periodic table, at the bottom of a group, another way of saying that, as you move down a group, the ionization energy of an element decreases. It takes less energy to remove a valence electron from an element at the bottom of a group than from an element at the top of the group. But how about when we go across a period from left to right? Well, this is where we have to bring back our idea of effective nuclear charge. So if we wanted to calculate the effective nuclear charge for these three atoms, for the charge that a valence electron in each one of these atoms feels, the effective nuclear charge for nitrogen, a valence electron of nitrogen is +6, for oxygen, +5, for oxygen is +6, and for fluorine it's +7. So what this is saying is the charge that the nucleus of an atom of fluorine exerts on a valence electron of fluorine here, that attractive force is greater in fluorine than it is in nitrogen. So since that attractive force is greater, this electron right here is being pulled towards the nucleus more than that same valence electron in nitrogen. Since it's being pulled more, the amount of energy needed to remove that electron, the ionization energy, is going to be greater for fluorine than it would be for oxygen or for nitrogen. So the general trend is, as you move to the right on a period, ionization energy increases, or as we move to the left, ionization energy decreases. So the general trend is, as you go to the left and as you go down, ionization energy decreases. So elements in the bottom left have the lowest ionization energies, Elements in the top right have the greatest ionization energies, meaning it takes the most amount of energy to remove a valence electron. Now let's talk about electronegativity. Electronegativity is a concept that allows us to do a lot of predictions with how elements will bond with each other. So, what is electronegativity? Well, the definition that you need to know is electronegativity, which is also sometimes called electron affinity, okay, is a measure of a nucleus's ability to attract electrons to itself. Another way of saying that is electronegativity is a measure of how badly an atom wants to gain or steal electrons or hold on to electrons. And what we can see in this periodic table here, we have values, electronegativity values for different elements. Okay? We can see that the element with the greatest electronegativity is fluorine, up in the top right corner, and the element with the lowest electronegativity is francium, in the bottom left. So the general trend is as we go up and to the right, electronegativity increases. Follows the same trend as ionization energy, with one exception, the noble gases. Okay? The noble gases, we don't really measure their electronegativities. Xenon is actually the only, one of the only noble gases that forms compounds. There's some other, we've started making some krypton compounds as well. But xenon, we can form compounds so we can measure its electronegativities. But the other noble gases, they don't react with anything. They already satisfy the octet rule. So they don't really, we can't measure their electronegativities because electronegativity is a relative value. It's compared to other elements on the periodic table. So what this is saying is that fluorine wants to hold on or steal electrons much more strongly than any other element on the periodic table. Much more strongly than francium does, for example. Okay? Much more strongly than oxygen. Much more strongly than nitrogen. Okay? And these values don't have units. Okay? They're just numbers that allow us to relate the electronegativities of different elements. We can use these values to predict bonding, what are called polar bonds and polar covalent bonds, which we will do next unit. But for now, we need to know what is the trend, which elements have the greatest electronegativities, which ones have the smallest, okay? And how can we explain that? A simple justification for when we go left to right, okay? Fluorine, for example, has 7 valence electrons. Oxygen has 6 valence electrons. Nitrogen has 5 valence electrons. They're getting closer and closer as we go to the right towards satisfying the octet rule. So since fluorine is so close, it only needs one more valence electron in order to satisfy the octet rule. It really, really wants to steal one. It really, really wants to find another electron from another element so that it can have 8 valence electrons and satisfy the octet rule. So it's going to have a really high electronegativity. Oxygen, on the other hand, has 6 valence electrons, so it needs 2 more. So it's still pretty close to satisfying the octet rule, but not as close as fluorine. And as a result, its electronegativity is a little bit less. We see on the scale 3.5, okay, compared to 4.0 for fluorine. And as we go to the left for nitrogen, nitrogen is now 3 valence electrons away from satisfying the octet rule, so it's not going to want electrons as badly as oxygen or fluorine, so it's going to have a even smaller 3.0 electronegativity.